Hello everyone, Mr. Rubo here. And today we're going to look at 10-18, 10-20, and 10-21. So for the first one, 10-18 has the problem circle A is tangent to circle B. See, we're drawn, they touch at point R. The circles are tangent to each other. Just make sure you read that carefully. PT is a common external tangent at points P and T. And then this angle down here is 41 degrees. So we're trying to find angle S. Now, when you look at this problem, you're like, okay, there's not a lot of information. But once you start actually like drawing in some radii and things like that, you actually get some information that'll help you. So the first thing you might notice is that since we know this angle here of 41, we know that PR, this arc, is 82 degrees because it's that inscribed angle, okay? And then you might be like, great, now what do I do? Well, let's draw in some radii. So that's at point A. And then we're going to draw the same thing from point B. And the reason why that's helpful is because that forms those right angles. And then we are going to connect A to B. And the nice thing with this is they also go through that tangent point at R. So they go through that there, which means if this is 82, this central angle is also 82. And now going to our knowledge of quadrilaterals, we know that in any quadrilateral, and so the quadrilateral I'm looking at here is PTBA, all the angles add up to 360. So if this is 90, this is 90, this is 82, we do a little bit of math and you get that your missing angle, pretend I know my angles, is 98. So angle B is 98. And now we use that same idea we did before where, we know what this arc is. This arc is also 98 degrees, which then means this inscribed angle is half of that. And we get our answer of 49 degrees. So, a lot of times, if you're unsure, draw in radii. Also, if you're unsure, if you have an angle, figure out the matching arc, whether it's inscribed or central or whatever it might be. But that's what we needed to do in this problem. Okay. All right, so let's keep it going. So 19 we'll save. This one you'll actually do a little bit of practice after pages 20 and 21. All right, so now for number one, we want to know, is this triangle scalene, isosceles, or equilateral? But all we know right now is these arcs. Well, the nice thing is they're all arcs, and this triangle's inscribed in the circle. So, once we figure out what the arcs are, whatever this angle is, it's half. Whatever this arc is, it's half. Whatever this arc is, it's half. Okay, so now to figure out what the angle is, well, we know a full circle is 360 degrees. So we can just say, let's add up all the arcs and set it equal to 360. Okay, and at this point, you would go and solve this for x. So you eventually get x equals -4. So make sure you do that work and try it out. And then once you solve it, you end up getting that this arc is 179. You substitute it in over here, and you get that this arc is 111. And the last arc ends up being 70. So that once we have those, we know all these angles are half of each one of those, but we don't even have to figure them out at this point because we know isosceles, equilateral is the same as an equiangular, so they would have to be all the same. Definitely not the case here. Isosceles, two of them would have to be the same. because the base angles are congruent in isosceles triangles, which means because they're all different angles, or all different arcs, the angles would all be different. So this would have to be scalene. So even though we're only told stuff about the angles or the arcs, and we can figure out the angles, we know it's a scalene because of the sides being all different. All right, number 2 here, equilateral triangle TMA with side lengths of 42 is inscribed in the inner circle H. If circles H are concentric, and the length of the larger radius is 12 more than the length of the smaller radius, find the radius of the larger circle H. So we have the 2 circles, both centered at H. So when you look at this, we can figure out that this whole side of AT is 21 because, not 21, pretend I did my math right. It's 42, getting ahead of myself. So then when we draw in some radii and then this altitude, because of the isosceles triangle, it breaks it. It goes to the midpoint, so that's 21. That's where I was getting. And one of the really nice properties with this, when you have an equilateral triangle that is inscribed in a circle, when you draw this radius, not only is it the radius of the circle, but it also bisects this angle. So this angle is normally 60. It's now 30 because it's bisected, and we have a 30, 60, 90. And if you do your ratios, you end up that this guy is 7 root 3, and then this is double that, so 14 root 3. The reason that's nice is because now we have the smaller radius, it's 14 root 3, and we're trying to find the radius of the larger one, which means we just take the smaller radius and add 12, because it is 12 more. Okay. So yeah, and that's kind of the big thing with today's part is a lot of those triangles that get inscribed or circumscribed. So we'll talk about that in a second. All right, number 3, and always, sometimes, never. The vertices of a triangle are concylic, which this means, and this is why this is here, it means that you can draw a circle around all the points. So it's kind of like collinear, where we're talking about all points on the same line. These would be all points on the same circle. So if the vertices of a triangle are concylic, then the triangle is equiangular. Well, I don't have to draw anything, because if I look at question 2, here's an equilateral triangle, or equiangular, because it's also equilateral, that is concylic. But if I go up to number 1, same exact idea, concylic, because all 3 points are on the circle, but it's a scalene triangle, which means not all the angles are the same. So it does happen, but not all the time. All right, last one on this one. Regular pentadecagon, which means penta is 5, deca is 10. So this is a 15-sided figure, is inscribed in a circle. Now, inscribed means that it's on the inside, the shape is on the inside of the circle. Find the measure of the arc cut off by the shortest diagonal in both degrees and radians. So it kind of has 2 parts to it. So first, you could try to draw a 15-sided figure, but I'm not very good at it. Obviously, my circle looks horrible. This is what we're looking for, though, is we're looking for the diagonal that connects, the arc of the diagonal that connects the shortest diagonal, meaning 2 vertices that are just separated by 1 vertex in the middle. Okay, so pretend there's 15 sides in this. We just care about this arc here. Now, the important thing is that it is regular, which means each of these parts is 1/15 of a circle. We want 2 of them, so we do 2/15 of a circle. We know a circle is 360, so 2/15 of 360 is 48 degrees. Now, 48 degrees is obviously our answer in degrees. Radians is another type of measurement for angles, and it's based off the radius of a circle. And so the way you convert, or really the big thing is that one circle is 360 degrees, well, in radians, a full circle is 2 pi. So I can do the exact same math and say, oh, 2/15 of 2 pi, and this is our answer in radians. So that's our conversion, is that one full circle is equal to 2 pi radians, and we also know one full circle is 360 degrees. So just different measurements like feet and meters, same idea. All right, number 5. Equilateral triangle, DEF, is inscribed in circle O, and equilateral triangle ABC is circumscribed. So you can kind of see the difference here. Inscribed means it's inside, circumscribed means it's outside, but the thing is it touches at those 3 points. It's tangent to those to that circle, okay, for all the sides. So EF is 6, so we know it's an equilateral triangle, so we get a lot of stuff there. We want to find CA. Now, CA, well, and it's actually really helpful that I drew this point in, because if I draw this, that's a radius. Well, I can also draw this, and that's another radius, right? So these two are congruent. And so if I do a very similar thing that I did on the last page, drop that altitude in, and we have a 60-degree angle because it's equilateral, that's split. So this is 30 degrees. This side is 3. And you do your 30, 60, 90 ratio, and you end up that this height is √3, and that means this is 2√3 for the radius. Once you know that's 2√3, you also know that's 2√3. Now you might be like, okay, great, now I'm stuck here, but I can continue drawing this up, so through D, and actually keep going all the way to A, because this is tangent, this is a right angle. And then it's the same idea. This is going to bisect it. So this equilateral triangle is now 30 degrees. So this is 2√3. This side would, I only care about A to this point. So that's double it. So that's 4√3. And then you double, pretend I paid attention. I even put it down. My right angle's right here, which means this side is 2√3 times √3. You simplify that, and you get 2 times 3, which is 6. And it ends up, because of the equilateral triangle, it ends up that if we do the same idea over here, we can draw it. I know it doesn't look great, but technically we can do the same thing over here, and this radius doesn't change. This is the 30-degree angle, which means this is also 6. So CA is 12. So again, don't look at the drawing necessarily. This ABC doesn't really look equilateral. It kind of looks isosceles, but we're told it's equilateral, so we know it's equilateral. All right, so then let's look at number 6. Given triangle DEF is equilateral if the radius of the inside circle is 5, then find the radius of the outside circle. So we kind of do a very similar process here as what we just did on the last one. And we know this is 5, and then this is the radius we're looking for, okay? But because it's equilateral, really nice thing is we get the 30, 60, 90, and so this is 30 degrees because it was 60 cut in half, so it's the X. This is a right angle, so this is double, so R is 10. Not a lot of work if you remember your 30, 60, 90 ratio. All right, last one. The inside square has a perimeter of 40. Find the perimeter of the outside square. So I know the picture's kind of off a little bit, but these are on the circle. Okay, it just wasn't super nicely copied over. So we know that each side is 10 because it's got a perimeter of 40. So let's go to the center. And the reason why going to the center is nice is because we know this is 5. And then if we draw in the diagonal, this is now the radius of the circle. Okay? Because it's going from the center to the edge of the circle, so that is the radius. And really nice thing is it splits this 90 degree in half. So we have a 45, 45, 90. So it's 5, 5, 5 root 2. And then once we know that, we actually know from here to here is 5 root 2, which that is from the center to the edge of the circle, which is, if you kind of expand it out, this is 5 root 2. So this is also 5 root 2, which means we get a side of 10 root 2, and it's a square, and we're looking for the perimeter, so we do 4 times that, and you get 40 root 2. Okay, and there you go. And so if you have questions, feel free to ask, but go back onto page 19 and work on that, and have